Good evening and welcome you all for today's lecture. I'm Kamala Gunwadhan again, a council member and the chairperson for the Knowledge Sharing Subcommittee of Civil Engineering Sectional Committee. I think there are new participants today in this forum, and I will brief what are our schedules from Civil Engineering Sectional Committee and our future, very recent future plans. Basically, we are organizing these presentations from Civil Engineering Sectional Committee. On Tuesdays and Thursdays are technical presentations. Actually, today is a Tuesday. We are exclusively reserved Tuesdays for series of lectures from under medium rise buildings, designs and constructions by Professor Tishan Jayasinghe. We started this program on end of 2021, last year, December, and we have already done with 4 programs, webinars, together with overview of the history of civil engineering in Sri Lanka. That's the introduction lectures Professor conducted. Under this medium rise building designs and construction series, our number 1 presentation was an overview of medium rise buildings, designs and construction. Number 2 was structural design methodology. Number 3, the design philosophy for medium rise buildings, about 10 floors. Number 4 was design philosophy for medium rise buildings of 15 to 20 story range. So Wednesdays we have planned to arrange non-technical presentations, and we have done with 3 presentations so far. Our main focus for Wednesday programs are to organize member development programs and some public awareness programs, where our civil engineers can assist, support even the public. Out of these, you all can share things that to develop your instincts, your insights, and also to develop your professionalism while achieving a better living standard. This is what we need to focus on Wednesdays. Actually, we are receiving very good responses from our resource persons whom we have invited for our programs. And they are actually eagerly waiting to share their experiences with all our participants. So that's a great thing. Civil Engineering Sectional Committee will do our best and deliver stuff for your benefit with the leadership of Professor Jayasinghe. On Wednesdays, our first presentation was Samajiya Tirasara Sangwardhana Engineer Wage Karya. It called Engineers' Role in Execution of Community Sustainability by Engineer Dr. Laksit Pradeep. And second one was a good one again, Magic of Thinking Big from Engineer Dr. Ranil Sugatadasa. And third one was Entry of Engineers to the Larger World of Decision Making. It was done by Engineer Shanta Kamaladasa. So Thursdays we have designed for multidisciplinary technical presentations, and number of professionals are now actually, even now we have identified. We have done with 3 programs up to now. Thursday's number 1 was Blast, 10 Structures Resist. That was done by Engineer Dr. Lakshita Fernando. Number 2 was Bridges and Flyovers, again Professor Jayasinghe, under the title An Introduction on Sri Lankan Scenario. And number 3, Awareness of Civil Engineers on Professional Review Process and How to Face Confidently by our past President, Engineer KPIU Dharmapala. As a briefing, what we have done so far, and I will remind you about our next week's plans. Let me come back. for our presentations again. You can join the webinar tomorrow by Engineer Brigadier KDA Pereira on the topic Suitability of Standard Bidding Documents, which is a well-chosen title subject for our civil engineers. I hope you will get that advantage. Thursday, day after tomorrow, we are starting this is a very interesting topic. People have been requesting us. We are starting the first lecture about the design and construction technologies used in Central Expressway Section 2. Actually, this is the first expressway project that fully accomplished with local resources, including financing, designing, design reviewing, construction monitoring, supervision, project management, so on. All these things are done by a local team of professionals. This will be continuously, we will share our knowledge about the various aspects of highway constructions in the industry, especially including expressways. We will mainly focus on expressways under this series. Engineer Cellular will be conducting day after tomorrow. I thank Engineer Manjula Samarasinghe, Subcommittee Chairman, for taking a lot of interest to make these programs a success under the guidance and the support of Professor Teshan Jaisinghe, Chairman of CESC. Actually, this has become a reality, definitely, because of the other assistance of respective subcommittee leaders. We have to thank them. That will be done end of the project. Professor Jaisinghe's time, actually, I took a few minutes now to brief this because I thought this will be useful for you all, because those who couldn't join with the physically up to now, you all can refer the YouTube and you can update your missed previous presentations. Yes, everyone. Now, before we start the thing, actually, I'll mention about the today's thing also. We are starting the today's event after some announcements, and it is
Engineer Kamala, I'm now on.
Thank you. It is an honor for me to make this instigating note, even though you are now sure the speaker today. He is a veteran in this specific field, and he has taken the challenge of giving you the best knowledge, best know-how about the design and construction of medium-rise buildings under many key areas. He is again Professor Teshan Jaisinghe, Senior Professor of Civil Engineering at the University of Moratuwa. Today's topic is transfer structures for medium-rise buildings, and is a continuation of this lecture series. Without further ado, I call Professor Jaisinghe to take over. Before that, Professor, can I ask Engineer Manjula whether he has any announcement to do?
Yeah, please do so. Please do so.
Yeah, thank you, everyone. Enjoy this evening with this important webinar. Thank you so much. Engineer Manjula, do you have anything to?
Yes, especially thank you, Kamal Madam and Professor Jaisinghe. And there were many requests to share the already completed presentations to our members. So to honor the request, our using sectional committee create a new YouTube channel so that you can look and watch all the previous presentations. Still, we are uploading the presentations. Few are already uploaded, and I have already shared the video link with this message. And please log into and put a like, and then you can receive update. That's the only message. And over to you, Professor Jaisinghe.
Engineer Manjula, there's a small technical problem. The laptop is a little slow. Just give me 1 or 2 minutes until I get it, get it going again. Because I leave from the laptop and rejoin. Right? I'm on phone, but I'm using phone and laptop both. Laptop for video and phone for talking.
Right, sir.
Just give me a little time.
In the meantime, there were many members. I think here also can provide the resource person their expertise to the Civil Engineering Sectional Committee to enhance our quality and enhance the quality and quality standards. So we request our members to join with the committee and give you active support. To there are many subcommittees in our section committee. So I have shared the details in our WhatsApp group.
Come on.
I will again put the WhatsApp group link also. Then you can join with our WhatsApp our team and give your full support.
Can you see it? All right. Okay. Now it's possible. Huh? Right. Right. Today we'll talk about transfer structures. So first we have to see why we need transfer structures. Angelo, can you hear me properly?
Yes, we can.
Yeah.
Yes, yes, very well.
Yeah. Okay. So basically, we have a regulation in Sri Lanka where it says to stop when we have buildings. Say we have a housing scheme in a say apartment scheme, then we need every house exceeding 50 square meters will need 4.8 meter by 2.4 meter area for car parking. So each house will need a car park. So if you have 200 houses, we need 200 car parking spaces, which means, to accommodate 200 cars, say we are having a 40-story, 50-story building, 50-story building. Each floor, we have 4 apartments. It's very common to have 4 apartments per floor. Very common to have 4 apartments per floor because you can have some arrangement like this. Focus. Where you get the core, something like that. So these are core area. And these are apartment 1, apartment 2, apartment 3, apartment 4. So we have 4 apartments. We have 4 apartments. Oh, why gone? Okay, I'll start it now. Sorry about the technical problem. So basically, I'll start right from beginning. Now, you can see in Sri Lankan building regulations adopted by Urban Development Authority, for every apartment, we need 1 car park. And the minimum size of the car park is 4.8 meters by 2.4 meters. But for larger vehicles, you need a few bigger vehicle parking spaces as well. So let's see, we are having 200 apartments in a building, and we are having 4 apartments per floor. So this is the arrangement. So this is one possible arrangement. So this area is the core, where you get lifts, the staircases, and any other areas that you need, like, for services, service shafts, anything. Everything will be in that area. And then you'll get 4 apartments because this will give all-round view for each apartment. So that will be a very attractive way of, getting 4 apartments per floor. But, in some instances, you get 8 apartments per floor as well. So what they do is, if you're getting 8, then these will be a small apartments, and the corner ones will be bigger apartments. So you can get 1 bedroom or 2 bedroom small apartments, fill in the gaps, whereas the bigger apartments can be on the corners. So if you have 200 apartments, you need 50 floors. So we have a building with 50 floors, and we need about 5 floors of car parking. So all these areas will be car parking. Now you can see a real problem. What is the problem? We need a lot of space here below the below the transfer structure, and we need some different space above the transfer structure, which means we need to have something to transfer the loads. So basically the problem is we can't have the same grid above and below. Above the car park we have one grid, below the car park we have a different grid. And above the car park, so let's take an example. We might have one grid, and the size of the grid can be something like, so this way we need about 5 meters. This way we might need about clear space of 7.2 meters, 8 meters or more. This way. So the center line will be 7.8 meters or more. So you get 7.8 meters here, and this say 5 meters. But when you are doing the apartment, we need partitions, so you might get rooms and you might go for a structure like this. That means we get small walls. So we might connect these walls by using beams. By using beams, we are connecting these. So we are creating a grid of beams. So once you have a grid of beams, we can support any partition wall. So this is one common arrangement that has been used. But later day, I can show you how to optimize further. But today we'll assume that, we are having an arrangement where 50 floors will be supported by walls. Walls can be about 1.8 meters of length, 1.2 to 1.8 meters of length. The thickness of the walls can be about 250 millimeters. And that will allow us to create a set of beams. And once you have a set of beams, we can limit the slab spans to about 4 to 4.5 meters. And a slab, generally we use a minimum slab thickness of 125, but sometimes we go for 150 millimeter slabs because we need good sound insulation. In apartments. If you have 125, the sound insulation level can be slightly lower. So you are going to have slabs of 125 to 150 millimeter thickness, and that will allow you to easily span something up to about 5 meters. But if you are having partition walls, you might prefer some secondary beams or some arrangement. But let's assume that we are going to get some walls at some spacing, but these walls are not going to coincide with the columns below. So we are having walls, and we are having lower columns at different locations. So what happens? We need a slab. So we need a slab. Then you have to ask, what is the thickness of the slab? 1.5 to 1.8 meters. That is the thickness of the slab. Now you have to ask two questions. First question, can we construct a slab of 1.8 meters, 5 or 6 floors above the foundation level? What are the problems you are going to get? You are going to get a huge weight. If the slab thickness is 1.8 into 24, something like 40 kilonewtons per meter squared. 40 kilonewtons per meter squared load will be coming. It can be even more. But I just got a value something like 40. You can see 24 into 1.8 can be more than 40, but let's say 40 kilonewtons per meter squared. What is the impulse load that you use for your slabs? Maximum of 2 kilonewtons per meter squared. So once you allow for partitions, 1 kilonewton per meter squared, still, but how much load we are going to? 40 kilonewtons per meter squared. So what will happen? All these slabs will fail. So we need extra supports for all these slabs. So you can see, even if you design a transfer plate, it's very difficult to construct it. So how do you construct it? What we do is, we'll cast about 450 millimeters thick slab or 500 millimeter thick slab that can take a load of something like rather 30 kilonewtons per meter square. So this means this slab will need a lot of reinforcement. You have to design that slab as a flat slab, which means a thick slab of 500 millimeters supported by large columns of 1.5 meter by 1.5 meter. At a spacing of something like 7.8 meters, at a spacing of 8 meters. Then what you do is, you will design the slab for all the extra loads, and then you have to provide additional reinforcement. Why? The first stage, you design the slab to carry the load of the rest of the slab, and the rest of the building is not there. So that is enough. After that, now already the reinforcement is stretched. Now you have to consider all the loads from above, which means you need another set of reinforcement, but now the slab thickness is 1.8 meters. What you have to do is, you have to provide the addition of reinforcement. You have to provide the addition of reinforcement. And you will see huge amount of reinforcement is needed. But now today you know the problem. What is the cost of 1 ton of reinforcement? 260,000 as the market price. But once you finish, you might charge 270,000 per ton. What will happen? Huge cost. Huge cost. So what is the ideal solution? Now, if you can actually have a structure without transfer plate, then that particular building can be fairly efficient. But the problem is, because you have to provide so many car parking spaces, you can't have a suboptimal car park and an optimum building. On the other hand, you cannot have a suboptimal building and optimum car park. Neither might work. So because of that reason, we generally go for transfer plates, although it's very, very, very expensive. So you have to always keep in mind, transfer plates are very expensive. If you have land, you can go for another car park, do something that might be cheaper than trying to optimize the structure in the car park and optimize the structure in the superstructure, the tower. When you try to optimize both, you will need a transfer plate. But on the other hand, if you have a lot of land that you can have car park, then maybe it's worth considering the fact whether it's possible to have a separate car park. And separate car park need not be a completely separate one. It can be part of the building. So you have the tower, you have the car park, and this is not optimum. And you have another car park area, extend the building. This is not optimum because you are avoiding the transfer plate. And then you optimize this and have a proper car park because you can have any column spacing in the extended car park. So that way you might be able to solve the problem. But most of the time, you can't control the project like that because either the land is not enough or the architect is not willing to have a separate car park. Then you will find architect wants both optimized. The architect like to have optimum superstructure, the tower, and optimum car park. And when you try to optimize both, you'll find now you need a transfer plate. But transfer plate, what is the behavior? What is the behavior of a plate? And what are the problems we encounter with plates? You have to understand it. Before we design and do whatever we want, first we have to understand. Now, what is the problem with the plate? How the plate behaves? Plate. Now, when you are doing highway engineering, when you have a plate like this, we divide the plate into a grid of beams. We don't analyze it as a plate. We analyze it as a grillage, a grid of beams. We say we have beams in both directions. And that's a good way of looking at a plate. So if you have a plate, then what do you get? You get shear in each beams. You can get torsion and you can get flexion. You can get flexion. So if you have 1.8 meter thick slab, what can you say about it? This is in tension, little bit of concrete is in compression. What is the rest? Rest is cracked concrete. Rest is cracked concrete. Concrete that is cracked up to the neutral axis. Is it efficient or not? It is not efficient. It is not efficient. But because we are having only one structure, one transfer plate, sometimes we don't worry whether it's efficient or not, we just have it. But you have to always keep in mind, thick slabs are not efficient. Why? They have huge amount of concrete, and this huge amount of concrete can add huge amount of weight, and all these weight will create a lot of bending moments, lot of shear due to the self-weight. So, but still you'll find many engineers design these transfer plates knowing very well they are not efficient. They are not efficient. The problem with a thick slab is any concrete below the neutral axis is cracked. And it's not doing any service except providing cover to the reinforcement or preventing corrosion. So you have to always keep in mind that we are having a very inefficient structure. Then how do you design it? Now, if you want, you can model this plate not as a grillage. You can model it using plate elements in ETABS or SAP or MIDAS. You can use MIDAS, SAP, 2000 or ETABS. In all these programs, they have shell elements, and you can use shell elements, and shell elements will give you a proper connectivity, and shell elements have 5 degrees of freedom at each node. And so once you connect it, you can get bending moments, shear forces, and bending moments, shear forces, and torsional moments. So first question, what do you think about torsional moments? They are not a problem at all. Why? When you have a thick plate like this, the shear flow occurs around it. Shear flows like this, torsional shear flows like this. And here you can see it's 1.8 meters of thickness. So you get a force F here, force F here. What can you say about the lever arm? Maybe about 1.5 meters. If the lever arm is 1.5 meters, what can you say about the torsional moment carrying capacity of a slab? Very high. You don't need to worry about torsional moment carrying capacity, because the moment you provide flexural reinforcement, cut control in reinforcement, the torsional shear will not be a major problem, but you can always check it. Check it and see whether torsional shear is too much or not, but generally it's not a problem. Then what is the problem? The problem is flexion, because we are putting concentrated loads, the loads of 50 floors coming at as concentrated loads on to the slab, concentrated loads onto the slab. So what will happen to the slab then? you will get bending moments, and because you have 1.8 meter thickness or 1.5 meter thickness, you can always design the slab to carry whatever the bending moment you get, because it's a huge thickness, 1.5 to 1.8 meters. And I have seen some projects, they have even gone up to 3 meters thick transplant plate. And in one building in Colombo, I have checked it. I have made a model of it. This was somewhere in 2006 or 2007, 15 years ago. And it was a design done in Singapore. They had 3 meter thickness for the transplant plate at certain locations, and certain other locations 1.8 meters. So basically you can see, cast in 3 meter thick concrete is not an easy task. And it's huge amount of concrete and huge amount of weight. So these are things we have to always think how to optimize. So basically you can see, flexure means we need reinforcement. And then how about the top reinforcement? Say we have a big bending moment, we have tension reinforcement here. Now here you get compression, but we need crack controlling reinforcement here. That crack controlling reinforcement is needed at the top. So you need a lot of crack controlling reinforcement, and all the codes carry some guideline on crack controlling reinforcement in thick slabs. On thick slabs, they give crack controlling reinforcement. And for example, in the bridge codes, they say, consider only the outer 500 millimeters and provide crack controlling reinforcement considering a thickness of 500 millimeters. So depending on the code of practice you are using, you have to refer the special clauses they have given to find the reinforcement for crack controlling. The reason is, if you consider the full thickness and provide the crack controlling reinforcement of, say, if you are using British codes, 0.00, so that's 0.13%, 0.13%. Because the thickness is high, you will still get huge amount of reinforcement. You still get huge amount of reinforcement. So because of that reason, you have to always think carefully. So that's one penalty. So you have to control the crack, because otherwise this will crack. After construction, thermal cracks, early thermal cracks, all kinds of cracks can occur. So control the cracks. But because tension reinforcement is there, bottom, there's no problem, because there will be plenty of reinforcement in the bottom. Then what will happen? At each column, what will happen to the slab? Now slab is going to bend in the wrong way. Slab is going to bend in the other direction. That means now you need top reinforcement above the column. Top reinforcement above the column. So you need a lot of that. And then what will happen? Then the biggest problem in the slab is shear. The slabs are not very good in carrying shear. So what do? We provide reinforcement in the slab. To carry shear, these are vertical reinforcement. So you might get vertical reinforcement in the slab, something like 20 millimeter bars at 400 center to center everywhere in the slab. You are going to end up with huge amount of vertical reinforcement to carry the shear, because you don't like such a big load transferred without shear reinforcement. So what you do is you will provide 20 millimeter bars at 300 to 400 millimeter centers. Now you can see there will be huge amount of vertical reinforcement. One advantage is this vertical reinforcement can be used easily to support the top slab, top mat of reinforcement. So there's an advantage. So basically these top reinforcement will be supported by these U bars that you provide to carry shear. So that is a good news. What is the bad news? You can't walk inside the slab, because you have 1.8 meter slab. If you want to go and do something, you can't walk inside easily, because there's reinforcement everywhere. You can't walk inside. So there are difficulties. Because of all these reasons, we generally prefer two other options. So don't go for a transfer plate just because you need two grids. Always consider two other options. Before you consider transfer plate as the option, you have to consider two more options. You have to consider two more options. What are they? Beams, transfer beams, or cellular transfer plates. Now, what is a transfer beam? You get a huge beam like this. Now, if you have a transfer beam, what is a better shape? The rectangular shape, rectangular or square? What is the better shape? A and B. Which is better? If you are using transfer beams, what is the better shape? Always we think the rectangular shape is the good shape for the beam. Is that right? Engineer Manjula, what do you think? Anybody again can give an answer? A or B? Can you hear me?
Yeah, we can.
Yeah, A or B? I mean, B. I'm asking simple question. Square shape or a rectangular shape? For a transfer beam, what is the better shape? The better shape is square. And you'll ask, why? Because always we learn the beams can be rectangular, but transfer beams, we prefer square shape. Why? The reason is transfer beams, there's no guarantee that we'll have the load on the beam in the center. Sometimes you might find the load on the beam, the wall is not at the center, but on a side, So what will happen if we apply a huge load here? What will happen to this beam? That is going to twist. The beam is going to twist. The beam is going to twist. Then if the beam is going to twist, we are going to get a torsional moment acting on the beam. And most of you wouldn't have designed a beam for a torsional moment. But beams can be designed for torsional moment, but beams are not very efficient in carrying torsional moment. So how do you make a beam efficient in carrying torsional moment? The torsional stress depends on the minimum dimension, not on the maximum dimension. When you look at the second moment of area, 112 BD cubed, which dimension determines the second moment of area? The bigger dimension is the governing one, 112 BD cubed. So the bigger dimension is the depth is governing. But when it comes to torsional stresses are determined by the minimum dimension. So if you have a huge beam, deep beam, very narrow, the torsional moment carrying capacity of that beam is very low. The torsional moment carrying capacity of that beam is very low. So how do you improve it? Make it square. So then you can say the minimum dimension and the maximum dimension are more or less the same. Then you will find the stresses, torsional stresses can be minimized. Torsional stresses can be minimized, right? So both Eurocode and British code both gives methods for designing for torsion. They are not very different, but you can easily master how to design a beam for torsion by looking at the example given in Moseley and Bungie. The book by Moseley and Bungie, edition 6 and edition 7, they give a method for designing for torsion. So if you want to design a beam for torsion, go through that example, that is a proper example, And if you follow that example, you can easily provide torsional reinforcement. But you have to keep in mind, torsional reinforcement is not going to be as easy as shear reinforcement. Torsional reinforcement can be T20 bars at 150 or 200 centers. If the beam is subjected to significant amount of shear, the torsional reinforcement that you get, the torsional reinforcement is the outer reinforcement, because torsion goes, the outermost reinforcement will be the torsion reinforcement. Outermost closed loop will be the torsional reinforcement, and that reinforcement can be in the range of T20 bars at 150 or 200. Huge amount of reinforcement. So always you have to keep in mind, if you are having a transfer beam, there is a possibility that we may not load the beam at the center. If you do not load the beam at the center, we'll get a bending moment. So because we are getting a bending moment, what will happen? So we get torsional moment. Because we are getting torsional moment, we have to provide torsional reinforcement. And these torsional reinforcement will be in addition to all the reinforcement needed for flexion. Then what is the advantage of a transfer beam? Well, we are not getting beams everywhere. We might get a beam every 4 meters apart, 4 meters apart, or we might get a beam 5 meters apart. And generally when you get transfer beams, we try to arrange the transfer beams in a grid. So arrange the transfer beams in a grid. What is that? What is the reason? When you arrange the transfer beams in a grid and have a 200 millimeter slab at the top, the torsional effects can be on the beam can be reduced to a great extent. But generally, when you are modeling, you don't model the slab. You will model only the beams. You will model only the beams. You will model only the beams, and then I have to ask a question. When you are modeling the beams, how do we model it? We model it as a dimensionless element. Whatever the size of the beam, we model it at the center line. We model the beam at the center line. This is the center line, so we put the beam there. We put the beam there. And we might find the wall is here, beam is here. And this is 0.6 meters. So center line of the beam is here, and we are having 1.5 meter wide beam. So 1.5, that is enough, yes. And let's say we have a wall 600 millimeters away from the center line of the beam. Then how do you model this? Model the support. What we do is, we break the beam here, we break the beam here. We can have a rigid arm. Rigid arm. Rigid arm means, you will have a section which is the same size as the transfer beam. And then you support the wall on the rigid arm. So what will happen? Once you create the model, ask it to analyze, now the model knows the loads are not acting at the center, they are acting with an eccentricity. Because the model knows the loads are at an eccentricity, now the torsional effect will automatically be transferred onto the transfer beam. So when you are modeling, you have to model the walls above the transplant at the correct level, the beams at the correct center line, and then if there's no connectivity, because they are not aligned, you can make them aligned by using rigid arms, where you are going to tell the program, I'm having some eccentric loading, and the eccentric loading is represented by rigid arm. Rigid arm is a beam having a fairly high second moment of area. Sometimes what we do is we put a small beam and multiply using set modifiers in programs. We multiply the I value. On the other hand, you can allocate a big section. When you allocate the big section, make sure that particular small section has no weight. You have to define a concrete without weight, because these rigid arms are not in the real structure. What will happen if you model with a rigid arm having a weight? You are adding extra elements onto your model, extra weight onto your model. So always you have to define a weightless concrete, and this weightless concrete has to be used to represent all the additional members which are not really there, but your model has got them. Now, this is what we call creating a mathematical model of the structure. We don't create the structure, we create a mathematical model of the structure. The mathematical model can be very different to a structure, or it can be similar to the structure. And last time I showed you how to convert a three-dimensional structure, which does not twist, to a two-dimensional structure. So this two-dimensional structure that I showed you last time is a mathematical model, it's not the real structure. But here what you do is, again you are creating a mathematical model, not the real structure. Because in the real structure, you have a big beam, but on the model we can not represent the big beam. So what we do is we'll use a rigid arm and support the wall at the correct location. So in doing so, we can easily induce the torsional moment on the beam, and that will be the real situation that you are trying to model. So it's very important that you look into this matter. Is that clear? Any questions on the chat box?
There is one question.
Yeah, what is that?
This question was kept a bit early. Do we need distribution bars to connect vertical shear reinforcement?
Oh, yes. When you have these bars, you have to ensure that the vertical reinforcement goes above the bars, because otherwise there's no anchorage for the shear. Shear is very important, that we allow the development of tension in the shear reinforcement. So develop tension in the shear reinforcement, you have to send it around another horizontal bar. So you have to make sure the U bar that you use to carry shear starts below the bottom reinforcement and goes above the top reinforcement. It's very important. Otherwise, there's no, that particular bar cannot carry shear. Because the moment you get tension, there's no anchorage for the bar. Always make sure this U-shaped shear reinforcement goes below the bottom reinforcement and above the top reinforcement. It has to be. So that's why, you get a lot of difficulties when you have huge transfer plates. And I'm always for avoiding the thick transfer plates because of these construction difficulties. And if you want, you can ask a top engineer like Samita Jayakodi. In the ICT tower, he did some 3 meter thick concrete. I can't remember it is a transfer plate or a pile cap. I think it's a pile cap of 3 meter, the pile raft. But again, you really don't need pile rafts in Sri Lanka. I will come to that in a different lecture when I deal with foundations. I'll explain why the pile rafts work in areas with reasonable soil condition, whereas it does not work in Sri Lanka because we have bedrock. So all those topics we can discuss later. But what you have to keep in mind is casting a thick concrete in Sri Lanka, because our temperature is high, is a real challenge. And to overcome that challenge, I have done some work with engineer Nuwan Senaka and engineer Myron. You can type MTR Jayasinghe and DEF on Google, and you can download a paper on how to control the cement composition to maintain sufficiently low temperatures, not exceeding 70 degrees, so that you can prevent delayed ettringite formation within the structure you are casting. So that's a very important paper. You can solve a lot of your problems that you encounter when you try to cast big sections. By referring to that particular paper, and you can freely download it. It was published on ISL in 2015. And one of the authors is engineer Nuwan Senaka, who designed the 77-story twin tower at what we call Address 606. His consultancy firm, he designed it. And he's one of the top engineers because he designed so many other structures that you see at Budgamo Road, Rajagiriya. Budgamo Road, Rajagiriya, you can see a lot of structures. And he also designed this Maga 1 building and so many other structures. And he has designed the tallest building in Sri Lanka, where the first tower will be completed in about 1 year's time. And they are still, the second tower is already done halfway, but they are taking time to complete the second tower. And at the end, they will connect the 2 towers with a helipad at the top. So that is once completed, it will be the tallest building in Sri Lanka. But at the moment, it is the tallest is 68-story Altea. So in the case of Altea, I certified that. And one of my top students has already designed the 77-story twin tower. And he's the author of this based on his MSc research and some of the other research done as undergraduate research by engineer called Myron, who has already completed the PhD in Queensland University of Technology. So basically, you can download that paper. It's a very useful paper. Read it. You can get a lot of information about how to control the temperature in concrete, especially in thick concrete. Right. So basically, I have given you very important clue. That is, when you go for transit beams need to be square, not rectangular. And the other important thing is, if you have walls supported not on the center of the beam, but with an eccentricity, that must be clearly represented in the model. And I have shared one of the presentations that I used, a PowerPoint presentation. I used one of the PowerPoint presentations on the second lecture. And that PowerPoint presentation, you can get some diagrams. And another day, I will show you those diagrams so that you can understand it better. But today, now I have covered this one, beams, and I showed you how to be careful. Now the cellular transfer plate. What are the advantages? There are many advantages of cellular transfer plate. What is the first advantage? It's lightweight. Why? We are having a top slab and a bottom slab, but we don't have. The center is empty at many places. Center is empty, so we can save a lot of, and we can avoid the torsional effects. So what we have is something like this, and we have beams. Now the beams need not be square, they can be rectangular as well. What is the reason? The torsional shear will not go like this, but it will go like this. So you can see in bridges, we use I sections. We use I sections and construct bridges. And we say torsionless system. We say these I-beams are very weak, they cannot take torsion. On the other hand, we can have box sections. Like in Orogodowata flyover, Japanese Friendship Bridge, they are all this. What is the advantage? Very strong in torsion, very strong in torsion because torsional shear will flow like this. Torsional shear will flow like this. So very high lever arm. Lever arm is very high. So torsional capacity is very high in these beams. So the moment you create a cellular raft, the torsion capacity is very high. So you don't have to go for square. You can have rectangular beams. You can have rectangular beams because now the individual torsional carrying capacity of a beam is not that important. So then you'll need something like 350 to 400 millimeter slab. Why? Because the weight of the beams and the weight of the top slab will be carried by this particular slab. So we cast a slab, but you don't have to, the loads are lower because we are having voids. So the reinforcement requirement in a slab need not be very high. In addition to that, you can always prop about 2 floors below so that the loads can be shared as well. And then you get all these loads coming at different locations. No problem. Why? Generally, you select the beams, the transfer beams in the cellular structure at the locations where the walls are coming, from above. So that walls are directly supported by the rib, the web. Web is directly supporting the walls. That's one. So what do you need for the top slab? Generally, we go for 200 millimeter and we ensure it has 2 mats of reinforcement. We go for the top slab of 200 and we'll ensure it has 2 mats of reinforcement everywhere. Why? Because it's very useful to carry torsion. It's very useful to carry torsion when you have 2 mats of reinforcement because the slab is strong everywhere. That's a second. So here you will design this bottom slab to carry all these loads. And then you will get reinforcement, say R1. Then you consider the overall behavior, you get R2, you provide R1 plus R2. That is the bottom reinforcement that you provide. So this way you can easily design a structure. Very easy to model this. When you are modeling a cellular transfer plate, you can actually model the top slab and bottom slab and the beams separately. And generally the beams are modeled by using thick shell elements. You use shell elements to represent the beams, and you have to understand how to interpret the results, because now you are going to get stresses, not the forces, not the bending moments. So you might have to think a little bit when you are providing reinforcement. On the other hand, you can forget about the top slab and the bottom slab. Simply model the beams, but don't worry about the eccentricity. Do not worry about the eccentricity. You might get torsional moments. You can model as if it is a transfer beam structure, not a cellular plate. But all the torsional effects you can ignore. Because knowing very well, cellular raft can carry torsion without any problem. So you have to have a good understanding of the behavior of plates and relays when you are designing a transfer plate. And if you have a good idea, no problem, because once you ignore torsion, what you get is shear and flexure. If you have shear and flexure, you have a beam, no problem at all, because we all know how to design a beam subjected to bending and shear. We all know how to design a beam subjected to bending and shear. If you have any doubt, you can refer to book series by Mosley and Banji. If you want BS code, you can refer to the earlier versions. If you want the Euro code, you can refer to versions 6 and 7. 6 and 7. You can clear all your doubts because they have given a lot of examples, and it's one of the best books for you to understand easily, because you can also read the books by McGinley, but they are more complicated. They try to cover more complicated stuff. So if you are beginning, not that easy to understand the books by McGinley, but very easy to understand the books by Mosley and Bunch. So my recommendation is start with Mosley and Bunch's book. Once you are confident, read the book by McGinley as well, because McGinley's book covers various other situations that are more complicated, and if you want to be a real expert, you should have knowledge that is covered in McGinley as well. But I will try to cover as much as possible in this lecture series, so that when you read these books, you will be able to understand the contents of the books very easily. So any questions? So I will cover 3 options for transfer plates. One is the real transfer plate, which I don't like very much. Then the transfer beams that I like a lot, and cellular transfer plates that again I like a lot. And if I give the examples, we used there's a building called, it's under a big building in Nugegoda, 14-story building called Portia by Homeland Skyline. And then that building we use transfer beams. Then if you ask, what are the buildings that you have used? Cellular transfer plates. We use cellular transfer plates in Sky Garden. Mr. Seneca, Engineer Seneca used cellular transfer plates in Sky Garden. And then I used, he is the designer, I was the reviewer. And then I again helped Sanken Lanka to save a lot of money by going for a cellular raft, a cellular transfer plate in Cinnamon Red building. Cinnamon Red building is a special one because it is having 6 stories of car park. 7th floor you have the reception, and then restaurants and all kinds of things. And then you get a transfer plate at the 10th floor. And then 13 floors of hotel. 13 floors of hotel. It's a 23-story building. But the problem is, how do you cast such a massive amount of concrete at the 10th floor? Not easy. Huge weight. So when we talked about it, I proposed, let's do a value engineering for this building. Let's go for a cellular plate, cellular transfer plate. And then we did a lot of additional modifications, and we saved a lot of money from that building. So that is another good example where cellular raft has been used, cellular transfer plate has been used. And then, if you want a building with solid transfer plate, it is a Singaporean design, and that you can find in Crescat Monarch. Crescat Monarch. Crescat Monarch has a solid transfer plate. And then, how do you optimize solid transfer plates? There are the options that can enhance the performance of concrete, and one of the options is going for pre-stressed concrete. And that is another option. So there are so many different options. Today I have covered 3 simple ones, and I have highlighted the problems. So if you don't understand how to design for torsion, go through the book by Mosley and Banji, because there's no point in trying to cover that type of things in a lecture series like this, because we cover those things for our undergraduates. So all our undergraduates know how to design for torsion and so on. So they learn those things as undergraduates. So these at a higher level where we like you to become practicing engineers. But if you have any doubt, always refer the book by Mosley and Banji. And once you are okay with that, you are happy, then if you want further knowledge, refer the book by McGinley. That is also a very good book. It's a huge book. And then if you want further information, there are many other books. But most of those books are American books, but still you can read it. like, they cover deep beam designs, B zones, D zones, and all kinds of things are covered very well in those books. So by reading other books based on Australian practice and American practice, you can learn something, but always stick with whatever the books written for the codes that are using. And I'm sure shortly we'll all have to go for Euro codes. So if you're not familiar with Euro codes, start reading mostly. And I think still 7 is read 6, version 6 or 7, you can get a lot of knowledge and information. So do you have any specific questions?
Yeah, actually there was one raise hand situation. Now he's left, I think. It's okay. There are few questions in the chat box.
Yeah, what are they?
What about the maximum of preferred grade of concrete for transfer beams?
Yes. Transfer, if you are going for transfer beams, transfer beams are not a major problem. But what you have to understand is, we are using huge structures, huge sections. If you are using huge sections, you have to ask a simple question. Have we optimized the design? No, we are using huge sections because you want to make sure the walls are supported. Some of these walls can be staggered in the building. But still you want to have one beam supporting all these staggered columns. So what do? You increase the width of the beam and make it look big so that you can create enough number of voids. Rather than 2 beams, you will go for a 1 big beam. If you are using a 1 big beam, the question is, have you got an optimized design or not? The answer is not. It is not optimized. If the structure is not optimized, what is the point in using high strength concrete? No use. So if I am designing a big structure which is bigger than what I need, I will use grade 30 concrete, 30 megapascal concrete. I'll use 30 megapascal concrete, a maximum of 35. I will not using anything more than that. Why? To get high strength concrete, you need a lot of cement. Lot of cement means very high chance of exceeding 70 degrees. So don't use it. And then I will also define. I don't want high strength in 28 days. So these are all allowed in Euro codes. I don't want high strength in 28 days. I'm happy if I get, say, 30 megapascal in 28 days. Or I might even say 25, but it's a little on the lower side. But I might say, I'm happy, 30 megapascals in 28 days. And 40 megapascals in 90 days. How do you achieve that? You go for something like 20 to 25% fly ash. 20 to 25% fly ash. There's no need to use silica fume for low strength concrete. So you go for 20 to 25% fly ash. What will happen? You can delay the strength gain, because when the strength gain is delayed, low temperatures, and finally, but at the end of the day, at the end of 90 days and beyond, you are getting grade 40 concrete or 40 megapascal concrete. So when you are doing the model, you specify the strength of the transfer beams as 40 megapascal. But when you are casting only 30 megapascal concrete in 28 days, and you go for 40 megapascal in 90 days. All these options, different options are allowed in Euro code. That's why we like Euro codes. We prefer Euro codes than British codes. British codes are very restrictive, but Euro codes are far superior. And when you use Euro codes, you can make huge savings by thinking different. So that's why you have to read the books that tell you the fundamentals like Mosley and Banji, then you will gain the confidence of attacking the problems with different options available in the codes. And that's what we call value engineering. That's what we do. And we allow any engineer to do the designs, and then we say, I'll save you 30% of that. Then we go for the modern Eurocodes. We do all our designs according to that, minimizing the section sizes and so on. And then we save money. And the beauty of value engineering is whatever you save, 90% for the client, 10% for the 10% for you. And if you save 200 million in a 50-story building, your fee will be 20 million. And to save these, you don't need ages because the design is already done. What they're doing is doing some modifications where you are saving the materials. And every cube of concrete saved is a huge amount these days. Something like, because you are using special concretes, it can be about 24,000 rupees saving per meter cube. Every ton of steel you save is huge value these days because you are saving something like 350 to 370,000. It can even go up to 400,000 in some cases. So you are saving a lot of material and materials, and you are saving a lot of concrete. And if you are doing a government the project where you have done you have got somebody do the design, the contractor has already done the bidding and won the contract, and after that the contractor comes and tell you, I'll do value engineering. And if you, as the client, you might like it because now you are going to save 500 million or something like that. Then when the contractor saves 500 million, you have to pay. You cannot get all 500 million. Half the saving belongs to the contractor, half the saving belongs to the client. So that way, the contractor can easily pay. Out of his 250 million, he can pay the designer who has already saved 500 million. The designer's fee will be 50 million. So you can see, if you don't go for cutting edge designs, there's a chance that your designs will be challenged. And then you will find the clients will start going for the designers who are doing the value engineering, then coming to you. So that's why always you have to think positively, learn as much as possible, and go for advanced designs. That cannot be optimized by somebody else. So what is second question?
Yeah, Professor, this is the one who raised his hand. Do we need distribution bars in a of transfer plate?
No, basically distribution bar is a crack control in reinforcement, right? So basically what we do is we provide crack control in reinforcement, and it can act as a distribution bar. So the most important thing in a transfer plate is how to control cracks. So you'll find transfer plates, top mat, maybe out of 20 millimeter bars at 150 to 200 centers. Sometimes you'll find you need huge amount of reinforcement at the top surface to prevent thermal cracking. So that's the disadvantage of going for transfer plates, because you need huge amount of concrete. When you have huge amount of concrete, one problem is it's already cracked. Say 80% of that concrete is useless because it's cracked and below the neutral axis. Secondly, because we are using a lot of cement to control cracking, we need huge amount of reinforcement. So you have penalties on two fronts. So that's why I don't like transfer plates. I mean, I'm not against it, but what I always say is try the other options first, and failing everything, okay, if we can't do anything else, okay, let's go ahead with transfer plate. But if you have, I'm sure you'll find, sometimes you might completely eliminate the transfer structure by working with the architect and coming up with innovative solutions like some additional car parking space outside the building, connected to the building but outside. So you can have a suboptimal car park but optimum But because it's suboptimal, you can't provide all the car parking needs. So you will extend the car park outside the building, and there you will go for the optimum spacing for car park, because there is no restriction. On the other hand, you will find that that's not possible because land is not available. Then you go for the solution where some transfer structure is needed. So you first try whether you can use the beams, and you think beams are a little too much and problematic. Then you might go for cellular rafts. And when you have cellular raft, again cellular transplant, and you have something like this. Sometimes you find that you might be filling up some of these areas, and those areas are filled up additionally because you need those fillings to support the walls. And sometimes you might find one of these grid is completely filled up by concrete. Why? Because there are few walls, and so rather than putting beams here and there, you might find filling up one cell is much cheaper. So there are so many options. Always attack the problem with an open mind. Then you can always come up with a completely out-of-box solution that you can rank as an optimum solution. So that's how you have to do it. So don't think transfer plates are very difficult or anything. They are just like slabs, and we know how to design a slab. But the problem is these are thick slabs, very heavy slabs. So we should see how we can optimize. Is that all clear? Any response?
He's there. You can respond.
Yeah.
Yoga. Shall I go to the next question, Professor?
Yes, please.
Can we continue vertical service ducts through the transfer flow?
Yes, if you want, you can go through, because small voids will not be a problem, because you can see we can always make it cellular. But it's much easier, because this although you think you can have a duct, it's not that easy. It's always easier to divert the ducts, all the plumbing work above the transfer plate, and then fill the transfer plate with a 300 millimeter thick lightweight fill. Fill the transfer plate with a 300 millimeter thick lightweight fill. It is always better, because when you say you are going to cast a shaft, a void through 1.5 meter deep or 1.8 meter deep plate, not easy. It's very much easier to divert the bend the services and divert to wherever you want. Then you can have one big shaft and take all the services through one big shaft, rather than taking with so many different shafts. So that's what we generally do. And then we fill it up with 300 millimeter thick concrete, very easy. Lightweight concrete. Or form concrete. And if you want, you can easily contact this person. If you want anything on form concrete, you can contact Mr. Sisirat Precon Marketing, and he's very good with that. What's his name? Number not 777 687 321. You can contact Mr. Sisira. He's very good in innovating things, and his company is called Precon Marketing, and he will do all your lightweight fills, no problem. And he's one of the best people for that particular task in Sri Lanka, because he knows, he has machinery for doing fill at any floor level in any building, any floor level. If you want a fill in the 60th floor, he will do it for you. because he has simple machinery that he has made himself for that type of tasks. Okay, what is the next question?
Do we need to align web of transfer flow and walls?
Web of transfer, flow. That is cellular one. Is that right? He's I think talking about cellular one. Otherwise, there's no web. Web comes only in the cellular one. Yes, cellular ones. Better to try and otherwise, you can't support a wall on a thin slab. Always you need to have some kind of concrete fill inside the cellular one. So carefully select it. So we have to talk with architect and then initially select the arrangement of the transfer plate, whether it's a transfer plate or a cellular transfer plate or a beam slab type transfer beam system. So that all you have to select. But if you can't align it, in the cellular one, it's not a problem. Because you have all the torsional effects will be taken up easily by the cellular structure. Whereas in the case of transfer beams, they are not on the center, then you get torsion. So that's simple. Any other question?
Yeah, is there any necessity to add additional vertical reinforcement in between lift joints other than shear and torsion to control transverse shear to
Yes, of course. Generally, what we
joints
do
in stage
is
concreting?
What we do is sometimes we locally thicken the shear walls at the transfer plate level because we are getting huge beams coming and connecting to the shear core. So because of that reason, generally, if you have transfer plates, we don't use anything less than 300 millimeter thickness for the anything less than 300 millimeter thickness for the lift core walls. If you have a transfer plate, generally we use 300 millimeter thick walls for the lift core below the car park level at the car park levels. And then what we do is we temporarily, we artificially thicken the wall so that any local stresses can be easily distributed without causing any damage to the shear walls or the lift core walls. So it's a good question. It's a good practice. Thicken it. So if you have 300 millimeter thickness, you can make it 600 as a band. So all your transfer beams will be connected to the band, not to the wall. And band can always distribute the stresses evenly so that there will not be any adverse effect on the shear walls of the lift core. And also you will ensure if you do a proper analysis, you will always find concentration of stresses. So because of that reason, we'll locally increase the vertical reinforcement in the shear walls at the transfer plate level. So instead of having some 16 millimeter bars at 200, you might provide 25 millimeter bars at 200 at that level locally. Say 1.5 meters above and 1.5 meters below the transfer plate, you might have 20 millimeter bars, 20 or 25 millimeter bars at 200 centers locally. The idea is, you will have the normal 16 millimeter bar and you will tie an additional 25 millimeter bar. Why? Any local problem will be well looked after by the additional reinforcement. That's a good question. Any other question?
There are, but I don't know whether the participant is here. What about the allowable incremental deflection for the transfer plate?
That's a very good question. When you are designing the transfer plates, always keep in mind, transfer plate is not going to be loaded at once. Transfer plates are loaded with the construction sequence. That means you have to do a construction sequence analysis. When your ETAPs allow it, SAP allow it, SAP little difficult, ETAPs little easier, but you must do a construction sequence analysis, which means the program will consider that the building you're analyzing is not constructed at once. It is constructed stage by stage flow by flow, and then you will find the bending moment due to dead weight of the structure. Dead weight of the structure is higher than what you get just by doing a straightforward analysis, considering that the whole structure is available. So generally, I use a rule of thumb. I generally consider the bending moment due to dead weight, due to the self weight of the structure, will be increased by 50%, and the shear force will be increased by 25%. But when I say 50%, overall increase is low because you get live loads, dead loads, all. Then the live load moment will not increase because live load moment will not come until the structure is over. So because of that reason, we don't worry about live load effects, but we certainly will get the dead load effect coming step by step. And that means generally I consider the dead load moment will be increased by 50% when I do a design, and I might not even bother to do a serious calculation. But if you want, you can ask the program to do a serious calculation because that facility is available in SAP 2000 as well as ETAPS, and also MIDAS also gives that facility. And MIDAS is considered a very a really good program for construction sequence analysis. MIDAS is considered as a really good program for construction sequence analysis. And so many engineers generally use that program for construction sequence analysis. Any other question?
Yeah, quickly I'll go through. Can we start column from cellular transfer plate?
Yeah. So when in a cellular transfer plate, whenever you want to start a column, you might locally thicken the beam. Locally thicken the beam so that you can start a column. No problem. You can start it, but it must be on a beam. It must be on a beam. So if you don't have a beam, increase the size of the adjacent beam. That way you can bring the column onto the beam. Any other question? Hello?
Sorry, can you hear me? What about vertical steel plates with studs for shear? And again, with the same vertical steel plates to accommodate shear in transfer beams.
Generally, now we are talking about composite construction. Now, these days, I would go with one material rather than trying to mix up so many things and do things that are directly don't understand. Now, at the end of the day, whatever you do, you have to take the responsibility. So because of that reason, I would prefer to do things in the way that we understand, rather than doing experiments in a tall building, because if something goes wrong, what happened in Miami a few months ago, when a tall building collapsed, 150 people died. And do you know what is the reason for that collapse? It is because, they have not done a construction sequence analysis. So they have not increased the moment to allow for a construction sequence. Then what happens is, you complete the building, nothing happens because the building is new, everything is strong. But with time, the cracks, because now the bending moment is, you are not considered the increased bending moment, you have under-designed the structure. So what happens is, under-designed structures will have a higher crack width than the normal structures. And then through cracks, you get ingress of salt, water, and all kinds of salty materials. They form chloride, they will give rise to chloride attacks, and chloride attacks can create corrosion without showing any sign of corrosion. That is the biggest problem with chloride attacks. And we call it pitting corrosion. Pitting corrosion occurs without increase in the volume, so you will not see the deterioration of reinforcement. So that's why I have a simple rule: increase the dead load moment by 50%, because the actual increase is only about 25 to 30%. But transfer plate is a key element, and I have no hesitation to over-design the key elements. Because if a key element crashes, everything else collapses. So because of that reason, I have no hesitation to make over-design a key element. Now the time is close to 9 o'clock. Shall we stop?
Yeah, I think there are so many questions, but anyway, I will. Actually, thing is this from these participants cannot unmute themselves. I tried myself. I also couldn't unmute them. So sorry about it. And I think so. It's 9, almost 9. Shall we stop?
Yeah. So basically, I mean, when we start next day, they can ask some more questions if they have. So we can have a question and answer session before we start the next lecture next day.
Yeah.
So if you can collect the questions in the chat box, and then you can raise it next time. As soon as we start, we'll just refresh their memory, and then we'll answer some of the questions, and then we can start the next lecture. Because it's always it's always good to answer all their questions rather than
Yeah.
Okay.
So actually, yeah. Thank you, Professor. I want to actually not ask anyone else also to make this vote of thanks. So we had a very informative and very effective lecture. So a big thank to you, Professor, and
thank you.
Worthy lesson delivered. And I thank our organization subcommittees presentation sharing. Actually, we are doing now. So I extend my sincere thanks to ISL. With all these difficulties, they are also supporting this.
Yeah, actually, yes.
Really, without these participants, they are getting a good knowledge. And thank you for all your participations.
Actually, it's a little unfortunate. We had a little technical problem initially.
Yeah, exactly.
Because I'm having i7 computer, and today is the first day it became slow. Generally, it's a very fast computer. i7 new computer, but due to some reason, computer became extremely slow today.
Yeah.
So basically, and also I had to go for a urgent meeting today at Nigambo Hospital. So to help them out with some work. So
but we managed.
And thanks to the very good highway network in Sri Lanka, I was in Nigambo at 5 o'clock, and sorry, not 5, 6 o'clock. Even at 6 o'clock, I was in Nigambo, and I managed to come here by 7:15. So thanks to the wonderful job done by our Road Development Authority engineers. And today we are having a very good road network in Sri Lanka. And today I shared one of the WhatsApp messages showing some of the things they have done by Road Development Authority and the private sector companies in Sri Lanka. So if you have, I think you have already got that message, and you can share it with other engineers who are participating. If you can get their telephone numbers, I'm sure you can form a WhatsApp group, and then we can share this kind of very important information that actually shows that Sri Lanka, as Sri Lankans, we can do wonderful things if we start using our own knowledge. Okay, with that, we'll conclude it. Thank you very much.
Yeah, I have a small message. One participant wanted to get some geotechnical knowledge, and they wanted us to organize. But quickly, I have to thank Engineer Kriti Srisenanayake. When I put this message, he quickly sent me the link from Engineer Sahabandhu, who is doing organizing on 26th December, I think this month. I put that in the chat box.
January, 26th of January, or
this month, because they wanted to face the interviews for ISL professional review.
Right. Okay, very good.
Yeah, what he sent me was well matching. So it's a great support. I put it in the chat box. So
okay, right.
I have seen that.
Yeah, so and also for this lecture series, I'll be getting Dr. Nalindi Silva to help us, with some of the geotechnical lectures. I will also cover some geotechnical lectures. And also for Thursday program, we are planning to get who has done a lot of work on piling and so on. So we'll get so many lectures on geotechnical engineering as well to help all our engineers to improve their skills on geotechnical engineering.
Yeah.
Okay then.
So with all that, we thank you everyone. So thanks a
Yeah,
lot.
thank you. Thank you very
Night.
much.
Yeah.